So we should be happy. Okay, the same thing can work for someone. The difference between someone and everyone is that we want to translate them into different things. Someone is actually a lot easier than everyone. That arrow gives people a lot of trouble in the translation of everyone laughs. But with someone laughs, we want to have something of this form. Okay, we've got a different quantifier here. This is the existential quantifier, and it can be read in one of two ways. Or rather, this whole formula can be read in one of two ways. We can read it as for some z, z is a person and z laughs. Or we can read it as there is some z such that, and again, z is a person and z laughs. And I read it both ways, and I don't know which one I use more often. Okay. So we're going to then go ahead and give an interpretation to expressions of this form for some z phi, just like we did before for this, for every z phi. And it's going to be almost identical. This is true if and only if for some individual x, the interpretation of phi with respect to the instructions to assign z to x is true. Okay. The only difference between that and every this is that here we use the word every. And finally, just like we had to have an interpretation for arrow, we need to have an interpretation for our logical and as well. And we'll take that to simply be the set containing the pair of true, true. If you look at the truth table for and, there was exactly one row that came out giving it true. If P is true and Q is true, then P and Q is true. So this is when P is true and Q is true, the whole thing is true. And so we put the cases that give us truth into our interpretation of and. Okay, someone laughs is then true, translated as there is a z, person z and laugh z. And that is interpreted as true if and only if for some individual z, person z and laugh of z is true. Now interpreted with respect to the instruction to assign to any occurrences of the variable z, the individual x. And that's going to be true if and only if for some individual z, sorry, for some individual x, this pair, the pair made up of person of z interpreted with our instructions, with laugh of z interpreted by those instructions, is a member of the set containing just the ordered pair T of TT. We'll use the same situation from before. A and B are people, C and D are monkeys, E is a pencil, A, B, and C laugh, D and E do not. And we observe that the sentence, someone laughs, is true. And we need to show that by showing that this holds for some value of x. In this case, we only need one value. It could be A, it could be B, C, D, E, as long as one of them gives us something where that is true and that is true, with that individual in place of x here and here, okay, then we've shown what we need to show. And we'll choose individual B. Could have chosen A, we're going to choose B. okay? So we need to then show that putting B in place of X makes this true. Well, putting B in place of X gives us this. Person of Z with Z assigned to B is true if and only if B is a person. That is, okay, and B is a person. And so we get that that's true. Laugh of Z with respect to the instructions to assign Z to the individual B is true if and only if B is a member of the set of things that laugh. That is, if and only if B laughs. In our situation, B does laugh. And therefore, this is also true. That means that the pair, the ordered pair made up of those two values, is the ordered pair T, comma T, true, comma true. That ordered pair is a member of the set containing it. And so this, which just was that ordered pair, is also a member of the set containing it, containing TT. Which means for some individual X, namely for the individual B, this is true. Which in turn means that the denotation of our formula for some Z, person Z, and laugh of Z is also true. Now we still have to calculate the meaning for some, the translation of someone, and we do that the same way we did for everyone. We assume that someone laughs translates as someone as a function applied to laughs as its argument, and that the result of doing that in this case is here. We get that by replacing, by putting this in place of something here. And so we can calculate that someone is simply going to be translated as this, lambda P for some Z, person Z, and P of Z. Okay, the last one we look at is no one. And you might think that we're going to do something very similar with no one. That is, translate it using a new logical quantifier no. But historically, that's not what people did. We could do that, and it can work, and it's very easy to do. But what people did instead is take no one laughs to be essentially the negation of someone laughs. That'll predict that no one laughs is true, just in case someone laughs is false. That no one laughs is false, just in case someone laughs is true. That's what negation does. It flips truth values for you. And our analysis, I'm not going to go through it in detail, is going to be done the same way. We have to have that negation in here, but otherwise it's very much like the analysis of someone. It's lambda P, negation of, for some Z, person of Z, and P of Z.